Good morning to all of you. In previous session, we have seen screw con stability test, okay, which can be used to verify whether the given system is stable or unstable. In today's session, we'll be discussing Fourier transforms. Okay, so here we'll be discussing Fourier transforms. So you might have already studied Fourier transform in mathematics subjects, right? So basically you might have gone through Fourier series as well as Fourier transform. In digital signal processing, we'll be looking at Fourier transform as well as discrete Fourier transform and fast Fourier transform. Okay, that is DFT and FFT. So the Fourier transform is one of several mathematical tools that is useful in the analysis and design of linear time invariant systems. We already seen Z transform as well as we have seen convolution, correlation, right? All these different tools are useful for the analysis of LTI system. So similarly, this Fourier transform is one of the tool for analysis as well as which can be used to design an LTI system. So basically this Fourier transform involves the decomposition of the signals in terms of various sinusoidal signal or complex exponential components. So basically, Fourier transform involves the decomposition of signals in terms of sinusoidal or exponential signal components. Right? So in as we have seen in the Z transform, the time domain signal can be represented in Z domain by using that Z transform, right? Similarly, in Fourier transform, a signal from time domain can be represented in the frequency domain, right? So this Fourier transform is used to represent the class of finite energy signal. Okay, so this decomposition of finite energy signal is also referred as the Fourier transform. So the Fourier transform or discrete time signal x of n can be represented or denoted as capital X of omega, and the formula for it, so we are taking the basically Fourier transform of discrete time signal x of n, and the formula for it is summation n is equals to minus infinity to infinity x of n into e to the power minus j omega n. Okay, so it is somewhat similar to the formula of Z transform. We have already seen the Z transform formula. The Z transform formula is x of z is equals to summation n is equals to minus infinity to infinity x of n into z to the power minus n. So in place of z to the power minus n, there is term e to the power minus j omega n. So z is replaced with e to the power minus j omega, right? The remaining things are similar. So this is the formula for what? The Fourier transform of discrete time signal x of n. Okay, so this formula you have to keep in mind, right? So as we have seen in case of Z transform, this Z transform is the reversible process. So we indicated it as x of n having Z transform x of z. So you can identify the inverse Z transform of x of z to get the x of n. So similarly, this Fourier transform is again a reversible process, right? So I'll just rewrite the Fourier transform formula here. The Fourier transform of x of n is simply summation n is equals to minus infinity to infinity x of n into e to the power minus j omega n, right? So this is the Fourier transform of discrete time signal x of n, which is denoted as x of omega, and as this is a reversible process, so you can indicate it as x of n having the Fourier transform can write capital F here. Okay, so x of n having Fourier transform capital X of omega, and from X of omega you can identify the signal, discrete time signal X of n, by taking its inverse Fourier transform. Okay, so the inverse Fourier transform is simply indicated as, so we are basically identifying X of n by taking inverse Fourier transform of X of omega. Okay, so the formula for this is again 1 by 2 pi integration 2 pi x of omega into e to the power j omega and d omega, right? So this is the formula for inverse Fourier transform. Okay, so x of omega is basically periodic with period 2 pi. So any interval of length 2 pi is sufficient for the specification of this Fourier spectrum, right? Or this signal spectrum. Okay, so therefore it has been indicated as 2 pi, right? So you can take any interval of length 2 pi to specify. So therefore lower and upper limit has not been indicated here of this integration. You can take any interval of 2 pi to specify this signal X of omega, right? So this is what Fourier transform is, right? So Fourier transform of discrete time signal X of n is indicated by capital X of omega, and the formula for it is summation n is equals to minus infinity to infinity x of n into e to the power minus j omega n. It is reversible operation, right? So you can identify the discrete time signal X of n by taking inverse Fourier transform of X of omega, and the formula for this is 1 upon 2 pi this periodic integration of 2 pi of x of omega into e to the power j omega and d omega, right? So let's try to identify the Fourier transform of the discrete time signal. So here is one example where you have to determine the Fourier transform of the signal x of n equals to 1, 5, minus 1, 3, 4. So origin is not given, so we can consider here by default, if origin is not given, so the first sample will be the origin sample, right? So the given signal x of n is equals to 1, 5, minus 1, 3, 4 with origin at first one. Okay, so the Fourier transform of x of n is, it will be indicated as x of omega, right? And it will be Fourier transform of x of n. It will be given as summation n is equals to again minus infinity to infinity x of n into e to the power minus j omega n. Okay, but if you observe this signal, so x of n is varying from 0 to this is sample at 0, n is equals to 0, it is at 1, this is at 2, this is at 3, this is at 4. Okay, so it is varying from 0 to 4, so I can take limit as n is equals to 0 to 4 x of n into e to the power minus j omega n. So if I am substituting the values of n here, so it will be x of 0 into e to the power minus j omega 0, so it will be e to the power 0 plus x of 1 e to the power minus j omega plus x of 2 into e to the power minus to the power minus j 2 omega, right, plus x of 3 into e to the power minus 3 omega plus x of 4 into e to the power minus j 4 omega. Okay, So I'll just substitute the values of x of 0, x of 1, x of 2, x of 3 and x of 4 here. So x of 0 is 1, x of 1 is 5, x of 2 is minus 1, x of 3 is 3, right? And x of 4 is 4. So that is the required Fourier transform. So x of omega is equals to x of 0 is 1, so 1 multiplied by e to the power 0, so it will be simply 1. So plus x of 1 is 5, so 5 into e to the power minus j omega. Next value is minus 1, so minus 1 e to the power minus j to omega, so sign will be minus e to the power minus j twice omega plus x of 3 is 3, so 3 e to the power minus j 3 omega plus 4, it is 4 e to the power minus j 4 omega. Okay, so this is the required Fourier transform. You can also simplify it by substituting the values of e to the power minus j omega, or by replacing e to the power minus j omega by cos and sine function, right? So cos omega minus j sine omega, you can substitute in place of e to the power minus j omega, right? Or you can keep it as it is, right? So this is the required Fourier transform of the given signal. So if just for example, if we have been provided with the same signal but the origin at different position, so just for it is at 1 5 minus 1 3 4, okay, and just for example origin is at this 3, right? So again, if we want to identify the Fourier transform of this signal, so it will be given by x of omega summation n is equals to, so it is the originate as this 3, so this is at n is equals to 0, this is at n is equals to 1, this is at minus 1, this is at minus 2, this is at minus 3. So we can vary n is equals to minus 3 to 1 x of n into to the power minus j omega n. And if I'm substituting these values, so it will be x of minus 3 into e j 3 omega plus x of minus 2 e j 2 omega plus x of minus 1 e j omega plus x of 0 into e to the power 0 plus x of 1 into e to the power minus j omega, right? So I can substitute the values of this x of minus 3, so x of minus 3 is 1, so it will be e to the power j3 omega simply, plus x of minus 2 is 5, so 5 into e to the power j twice omega will be there. X of minus 1 is minus 1, so it will be minus e to the power j omega, right? X of 0 is 3, so 3 into e to the power 0 will be 3 simply. X of 1 is 4, so 4 into e to the power minus j omega. Okay, so these two different for these two different samples or discrete time signals, we identified this Fourier transform. Okay, so here this Fourier transform is this one. Even again you can replace this e to the power terms by cos and sine functions, right? So this is how you can identify the Fourier transform of the given signal, right? So initially we identified when the origin at 1, right, and here the origin at 3. Okay, so this is how you can identify it for the different signals, right? So in next session we'll be discussing various properties of the Fourier transform, right? Thank you for joining this session.